Hey everybody, time for lecture. So we're going to talk deposition modes and we're going to talk about specific procedures for carbon steel and sheet metal. So if you're following along in your book, this is going to be in chapter 1. First we're going to talk about a couple of vocabulary words, I guess. So this is something that kind of I think I brought up briefly either in person or in one of my other lectures. Deposition modes. So there are actually 5 different ways that the welding itself actually happens. Those are called the deposition modes. Deposition is the depositing of the weld metal to create a weld. You hear things like deposition rate, that's the speed at which you can lay a bead, how much metal you're laying down per second or whatever. Deposition modes is how the metal gets melted into the weld. So you have 5 types here: short circuit transfer, globular transfer spray, pulsed spray, and then new modes. So we're going to go over and talk about each of these things. The ways that your welder is going to do these different modes or achieve these different ways of welding is determined by the magnitude and type of welding current, the electrode diameter, composition, the extension of your electrode, and the shielding gas that you are using. So all of those things come into play. So the first one, short circuiting transfer. Sometimes you would see it referred to as this GMA-S to indicate that you're supposed to be welding in short circuiting transfer. Now this is the kind of welding that we pretty much do all the time in the shop. Because of the tools that we're using and the gas that we're using, and et cetera, et cetera. I should be able to get to just adjusting a couple settings and some gas and stuff so we can try out a different mode at least once during our class time. But for now, pretty much everything you're doing is short circuit transfer. So in short circuit transfer, the electrode short circuits when it contacts the workpiece. So it touches the workpiece, short circuits, and then melts off and deposits into the weld joint. And the biggest things that determine your your deposition mode, sometimes they're also referred to as transfer modes. So if I switch back and forth between those, that's why. So the biggest thing that determines what deposition mode you're going to be operating at is the current range. And the electrode diameter, because remember that is related to the amperage, the actual current. So that's at the lower voltage range and with generally the thinner wire. But it goes up to 035. You're going to still be doing short circuit if you're using the thicker 035 wire, just because you're going to still be in that smaller voltage range and because of the gas that you're using. So it produces a small, fast freezing weld pool, can be used in all positions. Very good for sheet metal because it's good for thinner material. It's not often used for structural applications. So if you're doing something much larger, thicker, bigger, structural, you're probably going to be doing a different deposition mode. The next one here is globular transfer, which is a great name. This one, the electrode burns above the workpiece and kind of spatters into making the weld. So this produces a lot of spatter. It's just a little bit higher current range, but a lower wire feed speed. So sometimes you will actually accidentally get into globular transfer, and it's generally a bad thing. Sometimes they say it can be useful, you can be doing it intentionally, but generally it's a bad thing. It produces way too much spatter, and it's not a very good, stable arc. So that would usually be if you think that something wrong is happening and you're having trouble welding. So then spray transfer. This one, the electrode also melts off above the workpiece, but it's much more controlled, and the molten metal, instead of being very erratic, it sprays into the weld. For this, you have to have a pure argon or a very high argon content in your gas, at least 80%. I've heard different arguments about this, that you don't need at least 80%, but usually a higher argon is going to get you a spray transfer. And this is going to be also at the higher voltage ranges. This one is used much more in structural stuff, heavy industry. There's little spatter. The limitation on it is it's generally only used in the flat position because it's going to be like so big and hot. It's not very good for vertical or overhead or anything like that, or horizontal. And you can't use it on thinner stuff. Like the 10 gauge that we're using is 10 gauge is about 1/8 of an inch thick, so it's really going to be much too hot for anything that thickness. Another one is pulsed spray transfer. This one, unfortunately, we can't do at the shop because it requires a special power supply. If you've ever tried out any TIG welding, then you've probably encountered thinking about talking about pulsing. So it's basically the same concept but applied to GMAW. So the power produces a constant low level current and then periodically bumps it up to a much higher current on top of that background current. So that like melts the metal, doesn't melt the metal, melts the metal, doesn't melt the metal, but it's obviously occurring very, very quickly. So when it's at that background current, no metal is transferred into the weld pool. But at the peak of that current, when it bumps the current way up, then spray transfer is occurring. So it's like pulsing, spray transfer, not spray transfer, not. Now, this is really useful because you can use spray transfer, which is a really nice deposition mode. It's nice and clean. You can use it on thin materials and in all positions with the ability to pulse, which is really great. And then there's newer deposition modes. There's, Lincoln and Miller are the two big companies, and they both sort of have their own, they're always developing, trying to compete with each other and developing new things. So Lincoln has something called surface tension transfer. Miller has regulated metal deposition. And they're both pretty similar. There's something else called synergic pulsed and adaptive pulsed deposition. Great name. But they're basically just further developments on that pulsed spray transfer, more controls, controlling waveforms, just like adding in much more technology into GMAW welding. There's other elements. I mean, there's other developments that are being introduced all the time. Some of these, like the STT and RMD, you're gonna, there's machines out there in all kinds of different shops. We were talking a little bit about Long Beach. I believe they have the Lincoln. They have a surface tension transfer machine that I've tried over there. I don't know if it's regularly used by the students or anything, but some shops will have these new modes. Some shops are still going to have, your old weird Lincolns that you have to read the voltage with letters for some reason. So all of these are going to be out there when you're running around in the wilds of the welding world. So on from deposition modes there, we're going to talk about specific procedures for carbon steels. Chapter 8, if you're in your book. A couple of vocab words here. Ferrous versus non-ferrous. This is two different kinds of metal. Ferrous metal contains iron, that's the biggest thing, is magnetic, and has little corrosion resistance. It's good because it's high strength, can be used in high heat environments. That's everything that we are, unless we get into aluminum, but pretty much everything that we're working with is going to be ferrous. Non-ferrous does not contain iron, non-magnetic, but has more corrosion resistance, more malleable, usually lighter weight. So that's going to be aluminum is the big one. Something like bronze, brass, copper, other stuff like that. Anything basically that does not contain iron is non-ferrous. Anything that does contain iron is ferrous. So those are some good vocab words you might see or hear thrown around. And then a little bit of an understanding about the families of steels. Steel is actually, it's kind of a big word that covers a lot of different things. So we're going to be focusing on carbon steels today. And we're going to get into what this means, but these are just the general sort of overview of these family trees, if you will. We got carbon steels, we got low alloy steels, quenched and tempered steels, chromoly steels, and stainless steel. So those are kind of the different discrete families here. Now, carbon steels. What are carbon steels? They are steels that contain carbon as the biggest alloying element. They usually also have some kind of manganese, silicon, and some small amounts of other elements. But the main thing is they are basically iron and carbon. Iron is the thing that comes up out of the ground that you mine, and then combining it with carbon makes steel. So that's why you will hear stuff like terms like wrought iron, because back in the day we didn't have steel like manufactured the same way that we do now. So it was a lot more pure iron, or almost pure iron. It's just a little history lesson for you, I guess. So now we use steel, not iron. What we're using is not iron, it's steel. The melting point of carbon steels is 2,500 degrees Fahrenheit. And these carbon steels are broken down into more families in that family of carbon steel, classified by their carbon content. So low carbon steel is up to 0.14% carbon. This is also called mild steel. Now this is everything that we're going to weld in class is all in this low carbon, mild steel subfamily of carbon steel. Unless, again, I should qualify that, unless we're able to get into doing a little experiment with aluminum, which we may or may not have time for. But that carbon steel or low carbon steel, mild steel, that's a lot of what you would be welding in like general kinds of fabrication shops. So even though it seems like, oh, there's all this big families and stuff, still carbon steel is by far the biggest, or low carbon steel is by far the biggest, most common material that you're going to find out there. Medium carbon steel is 0.15 to 0.29% carbon. Then you've got high carbon, 0.30 to 0.59. The important thing to remember, even though most of what you're going to weld is in mild steel, as the carbon content increases, the steel becomes harder and more brittle, and therefore more difficult to weld. So it's just an important thing to keep in mind if you start to work in any of those other carbon steels. Now, the low alloy steels, remember we talked, because carbon steel is alloy steel, so the low alloy steels are going to still contain carbon, but they have more of these other alloying elements like chromium, molybdenum, nickel, vanadium, and manganese. So these alloying elements were added for specific reasons. You know, you're trying to get a metal that has a really good corrosion resistance but isn't still stainless steel. You're trying to get like a really tough steel. You're trying to get a really strong steel. You're trying to get different qualities out of these, and so you're adding in different alloying elements at different in different amounts. Then the family of quenched and tempered steels and chromoly steels, another little family. So quenched and tempered steels are ones that are hardened and tempered at the mill. So they're going to be treated basically at the mill, and they're going to come to you in a specific form. So tempering is a heat treatment process, if you haven't heard that. The important thing to remember about quenched and tempered steels is that they have been heat treated. Stuff has been done to them to get them to a certain state that is desirable for whatever reason. Now, when you weld them, you're adding heat back into it, and so that can totally cancel out all the benefits that has been created at the mill by heat treating this steel. So that's really important if you're to know, at least if you're working on a quenched and tempered steel. If you weld it, you have to at least be aware of that. You could weld and then go back and do a reheat treatment, or just know that you're going to have something different than what was originally came out of the mill. But the reasons you have quenched and tempered, again, improved strength, impact resistance, corrosion resistance. It's all different ways to get different steels that are doing different things. And your chromoly steels, these are going to be very high strength steels. They can be annealed, hardened, or tempered. So they can be heat treated. You can mess with them, play with them. But these are going to require special procedures for welding if you get into any chromoly steels, which might be like bike frames or maybe motorcycle frames. So that's a little bit less likely. Those are common ones. Of course, there's lots of different places you might encounter chromoly steels. So those are a couple of the families we talked about. The main one, again, is carbon steel. We're going to talk about some of the electrodes for these different families of steel. For carbon steel, the kinds of electrode are defined in this American Welding Society designation, A5.18, if you ever need to find that. but the class of it, the properties of it, they are defined by the properties the wire produced when used with a specific gas or gases. So the important thing for us to pay attention to is the pretty much this electrode here is the only one that we use at the shop, ER70S-6. So that's the one that we use at the shop. And we're going to talk about what those numbers and letters, what that all means. You're all familiar with different electrode classifications from, from stick welding, and if you've done any TIG welding. So this is just the way that we designate GMAW electrodes for carbon steel. So we get E for electrode, R for rod, just like with TIG welding. It means it can also be used for TIG welding applications, even though that would be a little bit odd because it's such a thin wire. And then you have these two X's right here. So these are going to be numbers, and they're going to designate the minimum tensile strength of the deposited weld metal. So someone, has tested this weld metal and determined what this minimum tensile strength is, and you put it in. This is what this electrode does and what it gives you. And then the S designates a solid wire. We'll talk a little bit more about non-solid wires a little bit later. And then the dash and the X here, that's the specific alloy and any deoxidizers that are in it that make up the chemical composition of that particular electrode. So ER something, S dash something. The one that we use the most is ER70S6 electrode. Rod 70 thousandths of pounds, 70 hundred thousandths of pounds per square inch. And then S is for solid, and 6 is going to tell you the specific alloy and any deoxidizers that are in it of that particular electrode metal. So these are some more different electrodes for carbon steel that have more deoxidizing alloys. You'll see the ER70 is very common. You'll just have different specific deoxidizing elements, different specific alloys. 70S, S6, S5, and S7 I think are pretty similar. If you go to your welding supplier, they're probably going to give you one of those if you just tell them you need some GMAW welding wire. Now for low alloy steel, it can look a little bit different. You have something very different here on that dash part. So this is a designation for low alloy steel. It's designating a specific kind of alloy for a specific low alloy steel, just so you know what that might look like. Now this is flux core electrodes for low alloy steel. So flux core electrodes are going to look a little bit different. There is an E here still for the electrode. There is no R because this is not a rod. This cannot be used for TIG welding because flux core electrodes are actually hollow tubes. So there's E for electrode, and then there's one X. This first X is the only one that tells you about the tensile strength in this case. And then the second X is going to tell you about the primary welding position. So 0 is for flat and horizontal. 1 is for all positions. So some of these electrodes are going to be specific to just flat and horizontal positions. So that's something that you do definitely need to look for. And then you have a T here, an extra letter. T is for tubular because that flux core electrode is a tube. It's just a metal tube filled with flux on the inside instead of like a stick electrode, it's just a piece of metal with flux on the outside. It's just the opposite. Same thing. And then this X here is going to tell you about usability and performance capabilities. It's the kind of thing that you would have to be looking up to find out what these specific ones mean and what you might want. And then this X here is the chemical composition of the deposited weld metal. So the easy way to recognize flux core electrodes is they got a T in here, they don't have an R in here. Otherwise, they do look fairly similar to carbon steel electrodes. Now, a whole nother kind of electrodes, again, something we don't use or encounter here at OCC, but this is something you might come across out in the wild. So there can be tubular electrodes that are metal outside and then a core of powdered materials, primarily pure iron. So that is different than a flux core wire where the inside is flux to create a shielding gas that shields that metal or that weld. This is a tubular wire that has powdered metals inside of it. So these are some different names for different metal cord electrode wires. They look a little bit different. There's no R here. There's some weird other letters in here. C indicates that it is a composite, a combination of some different things. R, that's R for rod, is not included because, again, it cannot be used as a filler rod for GTAW. So these are different than flux cord electrodes. This is not something that you, I mean, depending on what you might go into with welding, you might encounter it. But again, like, it's the kind of thing where if you go into your welding shop and say, hey, I need some electrode wire for GMAW, they're not going to give you this right away. So now we get into some more specifics for carbon steels, which you've already had a chance to try out last week, which is great. A couple of tips about if you're working on thicker metals. We don't encounter this at OCC because we're not generally cutting any of our steel with thermal cutting with using heat, like oxyacetylene torch or the plasma torch. But if you do have this oxide scale, this should be removed before welding because it's going to make problems within your weld. Good thing to know, you can remove it just like with a sanding disc or a flap disc on your grinder. You can remove it on a belt sander or anything like that. Any paint, rust, or mill scale, that's a heavier mill scale than anything we encounter on our materials at OCC. This should be cleaned, but I've mentioned, I think, before, you can weld through a little bit of paint, a little bit of rust, and a little bit of mill scale with GMAW, which is kind of the nice, useful part of it sometimes. But with paint or rust is really the stuff that I would try to clean up before you weld. And then oil coating from a mill. Sometimes you will, usually on tubing is when you'll find something super oily that's protecting it from rust, but you do want to remove that before welding. It will light on fire. It can create problems. So fire is generally, you want to be careful with that. There's these things you can use degreasers to clean that oil off, but you do want to make sure that the degreasers are all cleaned up and dried off before you weld there. That vapor can be a poisonous gas. So just be aware of what you are welding on. If you do weld on paint, that's also very hazardous and toxic to your health. So that's another reason why you should clean paint off. A couple of other techniques that can be employed for welding on carbon steels. Things like preheating, interpass temperature, and post-heating. So these are fairly simple. Preheating is heating weld metal to a specific temp before welding. Interpass temperature, there's a temperature range that the weld should be at before the next pass is made. Sometimes you need to bring it up to that temperature. Sometimes you need to let it cool to that temperature. And then post-heating would be heating it up after you're done welding, so it maintains a specific temperature for a specific length of time after welding. So those are going to be designated for you if they're necessary in a welding procedure. Probably, unless you're doing something on your own and you might need to make this up on your own. We're going to talk about welding procedures in a little bit. So these are used on some of the different steels more often. Remember I said that the higher the carbon content, the more brittle it is and the more difficult to weld. So some of the higher carbon content steels and definitely the alloy steels are going to require some kind of preheating or post-heating and maybe interpass temperature. Basically all that you're doing is you're controlling the rate at which your metal cools. Because your metal, as it cools, it condenses, it shrinks, And sometimes that can, in the more brittle metals, the higher carbon or the alloy steels, or quenched and tempered, some of those other ones, that can create cracking. So you're trying to control the environment of the weld to not have changes occur so quickly. That's the way that I think about it. So these are some different, percentages, sort of rules, general rules, if you will, about when you might need preheat or post-heat, and et cetera, et cetera. It's not something that we use at OCC, because we're using that mild steel and it's so thin, it's not something that's needed. So if you do need to employ this, though, the oxyacetylene torch is what is most commonly used. There are like temperature indicating guns. There's crayons or even stickers that will like turn color at a certain temperature. The crayons will only write when the metal is at a certain temperature. So there's different kinds of ways to determine the temperature, so you can control that. If you need more stress relief than just heating up one small part, like where you're welding, then you might have to heat the whole part in a furnace with obviously specific tools and in some different setting that has all of those abilities, because you can control the temperature and how fast it drops and all that stuff. So now for the low alloy steels, preheating is important because it prevents the formation of hard weld area grain structures. The need for preheating is determined by the joint thickness, the weldment restraint, any clamps or tools and stuff that you have to hold that weld in place, and then of course if you're going to be doing any post heating or not. Another general rule for you, if you are working on this on your own, if cracks occur, you should increase the heat, either the preheat or the post heat or both, or throw in an interpass temperature in heat as well. Generally, you cool the weld in still air, meaning like not in front of a fan. You don't want to quench it in water. That defeats the whole purpose. Sometimes you would even use a thermal blanket or another insulator to slow down that cooling. Usually slower cooling is better for this procedure. Now with your quenched and tempered steels, they have been hardened. They have been heat treated to harden them and then tempered, so that's basically a whole heat treatment process to bring them to a specific desired place. So therefore, any welding is going to change those desired properties, which can be a problem. You may need to make sure you pick out the right electrode, and you may also just need to find how this was manufactured and find out what the manufacturer says about correct welding procedures. Usually that stuff can be found online. So don't get too, all of this stuff here, you don't have to get too concerned about knowing all of it. This is all just stuff that you need to know exists and is out there for if you encounter any of these situations out in the welding world, in the wilds, then you can know, okay, I've heard of this before. I know I can't just start welding it right away, and I need to figure out what I need to do here. Tooling, generally for any of these carbon steels, you can use copper, aluminum, or stainless steel tools, like more than just your clamps and stuff. You can make whole tooling jigs and buy whole tooling setups and have a lot more than just, a couple of C-clamps and vice grips. But sometimes cooling is necessary. We talked a little bit about shrinkage and stuff, so the tooling can be really important for that. It cools the material down by just having a heat sink where the heat can go into, so that can be really necessary and important. Another thing that you might find useful is a liquid anti-spatter spray. So you could spray that on the weld area where spatter might be, and it just kind of prevents all that spatter from sticking to the weld metal, which is nice, because then you can just kind of brush it off. You don't have to worry about wire brushing or if it's going to mess up your paint, if you're painting it afterwards, something like that. We don't have any, I don't think we have any of this spray at the shop. We might, but we do have a dip that you can dip your nozzle in. So if you remind me, if you want to try that out, I can get it out, and that will help to prevent the buildup of spatter inside your gas nozzle. If you're designing any of your own tooling, and that can just be, welding together pieces of metal that you need to clamp your pieces of metal to before you can do the weld that you want to do. A lot of welding is preparing for the weld that you're trying to do. A friend of mine used to say it was something like 10 minutes of setup for every 1 minute of welding or something. And that's something that that I have, had to learn, and I do in my shop. I definitely make my own tooling, which is just jigs and things to clamp to keep my stuff where I want it to be. It'll help to get the correct weld joint alignment. It controls the heat there, like I said. You can control the shrinkage better. Sometimes you have tooling that prevents, that controls the atmosphere. You have tooling that has gas on the back of your weld. It can help you to take apart different parts better. It's just, there's lots of different reasons that you would need to have different kinds of tooling. So now with carbon steels, not something that we have to encounter, but I wanted to go over a couple different things that you might see even in carbon steels if you're welding out somewhere else. You might have to do what's called plug or slot welds. Basically, it's two pieces of metal on top of each other. One of them has a hole in it, either just a single hole drilled or these slots milled out, and you want to be welding those two pieces together. So you're just going to fill in that hole, basically. So you kind of treat this like a fillet weld, where you just have to weld a whole weld all the way around the inside. You should be able to weld in one pass. The big problem with welding like this is lack of fusion at the weld root. So you'll weld all to the top plate basically, and won't get that fusion down to the bottom plate. So you can sometimes need to have a really aggressive gun angle to really make sure you get in there. That's going to be the best way to avoid that, and maybe kick up the voltage a little bit, is something that I do pretty often. So welding procedure, I mentioned this a little bit before. If you're welding in a shop or a place that has to follow certain codes, you're going to have different welding procedures that you have to follow in order for your welds to be okay. The welding procedure is going to designate a lot of different parameters. You're going to be told about your electrode wire, what gases to use, the deposition mode that you need to use, the parameters, what your voltage is, what your wire feed speed is, and you have to set up your machine for all of that. You have to install all the correct filler metal, make sure you have your drive rolls set up well. You even can be told make sure you have the contact tip, but you can be told the diameter of your gas metal. You can be told the shielding gas flow. All these different things are going to be designated in this welding procedure. You might also have cleaning requirements, wire brush before this next weld, or you might have heating cycles, that preheating and post-heating and stuff like that. So usually you'll want to, if you are establishing a welding procedure on your own, if this is something that you needed to do for your shop, or you needed doing a bunch of different repeating the same weld, and you have to make sure that this weld can pass code, you can make up your own welding procedure, and then you will have to make a test weld, and then you use destructive testing to check that weld, and if it doesn't have cracks, if it has proper fusion everywhere, then that means your welding procedure is good to go. So you're either going to follow those, or you may at some point have to set that up yourself. With the 212 class, we do actually have a little welding procedure form that we fill out, and you're kind of going to make up your own. Now, a couple specific things about sheet metal, just because that is a little bit different because of its thin. Sheet metal, you could be steel, stainless, aluminum, any kind of material, ferrous or non-ferrous. But you determine the thickness it's called the gauge. Well, we have 10 gauge and 16 gauge. Something important to remember is that steel, stainless, and aluminum all of their gauges are going to be different. So 10 gauge stainless steel is not the same as 10 gauge carbon steel. I just want to point that out. It's very annoying. Sheet metal is often used in for HVAC systems, for cars and trailers, and for small parts, sometimes for corrosive environment applications for like acids and stuff like that. But it is something that is, if you get into it, there's whole realm of like where you're just welding sheet metal all the time, and it does have some differences to, other carbon steels and different things that you have to consider. So this is just a nice couple of charts. It's sheet metal gauge thickness we have mild steel, aluminum, galvanized, and stainless. So you can have that as a quick reference to check what you're welding on. A nice thing that you might want to have if you get into sheet metal welding is a little gauge checker like this. Each of these slots is numbered for a gauge, and so you can slip it over the metal that you have and say, oh, okay, that's 10 gauge. And then on the other side, it shows the gauge number so you know what you're dealing with. So for sheet metal, you're generally going to use the short circuit transfer mode, the mode that we use in the shop most of the time. You can, as I mentioned, use the pulsed spray transfer mode for sheet metals. You have to have a fast travel speed. And of course, in order to get that pulsed spray transfer mode, you have to have a special power supply. A good rule to follow is you want to have a smaller wire size. So like I said, the 025 is better for welding our 16 gauge stuff than the 030 is. And a decreased wire feed speed can also help. Sometimes a lower percentage of CO2 in the welding gas mix, but not something that you guys change at the shop at OCC. We did talk about this in class last week, so this is good. Just a reminder, distortion and burn through. So distortion is as the metal heats, it expands, and then it moves out of position. I showed you that in the butt weld and use those clamps to pull it down. And then this one here is another thing where it will move closer together. So remember, you tack it on both sides. I always tack welds on both sides, or even a couple places in the middle if you want before you weld them. With a fillet weld like this, you'd want to tack it on both sides this way. So you would go, if your weld is like this, you go attack here on this side close to me, attack here on this side close to me, and then attack here and attack here. Because with that kind of weld, it's going to be pulled off center like that. Okay, so you need to make sure it stays at a 90-degree angle. And then another thing, if you have a big long weld, you can have your work drawn in a curve like that. So clamping, tooling will help with that. And then burn through, we talked a little bit about penetration versus burn through. We don't want that look of burn through, what's sometimes called sugaring in TIG welding. We don't really quite get that same effect, but we don't want burn through, we do want penetration. A couple of good tips to reduce distortion. Clamps, lots of clamps. You can never have too many clamps. Several small tack welds, very good practice to get in the habit of. Short weld beads instead of longer. We do, of course, have all of our welds are going to be 6 inches because we want you to get the practice of having to do those longer welds because they can be harder. But if you're doing something super long, a couple feet or something, you can do these short what's called stitching welds. You could even do on the other side, you might do a weld here like offset and a weld here instead of a weld on the exact opposite side. And that will help you to keep stuff straight and reduce all kinds of distortion. Other tips, let the metal cool between welds. If you're putting, welding multiple things onto one thing, do one weld, let it cool, then do another weld. My favorite thing is to weld in different areas of the project. So if you're welding up a square, something like this, I would weld on the corner here. Well, first I would tack everything heavily. So I go tack, 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 and maybe tack this side. I'm moving around a lot, tacking everything. And then I would move around a lot to do the actual full weld. So I might weld this corner, and then I'd weld this corner, and then I'd weld this corner, and then I'd weld this corner. So moving around on your project, that's just spreading out the amount of heat that you are using. So it really does help with distortion. A backing bar or plate, something big to clamp your material to absorb the heat, draw the heat away. Beveling butt welds, we talked a little bit about beveling last week because we have such thin material, you don't have to, but that can be a way to reduce distortion because it flattens the bead profile, doesn't piling up on top, and has more penetration and spreads that heat out a little bit more. For reducing burn through, it's a little bit more common on the thinner metal. Forehand or push welding is a little bit better if you're having trouble with some burn through. Maintain a short tip to work distance, so keep really close to the metal is actually better. So when you pull farther away, it's kind of like pulling away with a hose where you're spreading out that amount of heat on a larger area. Do these short welds with the gun trigger on and off. This might be harder. It's probably going to be harder to do and get a good solid weld that looks consistent. So this would maybe be used on even a thinner sheet metal than the 16 gauge stuff that we use. But any kind of anything you can do to sort of control the heat or stop the heat is good and useful. Another specific things that you can do with sheet metal is what's called spot welding. So you can use these kind of different tips on welders similar to the ones we have in the shop, or you can have a specific spot welder. You might have seen some of these in different shops before. So when you don't need one big weld bead, you just can have a bunch of tacks to tack the metal together. Use pretty much only in sheet metal because other metal is going to be much too thick. You're not going to get a good actual tack. So if you're using a machine like similar to ours, it has to have a timer on it. You can add that on or buy a machine for that. But usually this is what's very common to see, especially in like auto body shops or where you're doing stuff with sheet metal. You use it often in lap joints, so you'll have the metal overlapping itself like this, and you put those 2 points on either side, and you press down that handle, and it just basically melts the metal in between those 2 points, so it melts it together. It's not adding any material. If you're going to do it, your contact area has to be clean. If you have scale or rust, it's going to prevent fusion, especially be careful of the surfaces that are being fit up, because if you have something in between there, you need to make sure you clean that first. A problem could be gapping if you have it, offset a little bit, or you start adding heat and then your metal moves around a little bit. Lots of clamps again, and hammer it down again after each tack. If you're doing lap joints with different thicknesses, you want the thinnest material on top. If you can't do a tack weld with it, then you'll change it to a plug weld. If you're doing corner joints, which you can do not with that machine like this, but with different machines, you have to make sure they fit up super, super tight. So that is it for the lecture. So you guys hopefully will be watching this sometime during the week. And if you have any questions at all, you can email them to me anytime. I might save them to talk about when we meet up in person if I think it's something useful to talk about together, or you can just kind of jot those down and we can chat about them in person when we get together on Thursday. So I hope to see everyone. Remember, has to sign in on Thursday. And then, I'll just kind of check in with you all, see how it's going, and then we'll be good. And then we will get together on Friday. And then next week, just to throw this in there, next week is our midterm. It's not going to be a lecture next week. We'll talk more about the midterm on Thursday and on Friday, of course. And that's all going to be online. So you're going to do that all on your own. It's multiple choice. It shouldn't be anything too intimidating, hopefully. All right, that is it. See you on Friday.